Look at this data. What was the Kc value for the system in the original equilibrium? Remember that NO2's concentration must be raised to the power 2 because of the 2 coefficient in the balanced equation in front of NO2. What was the stress which was applied, and what did that cause, and what is the new equilibrium constant, and what do you notice? Again, the Kc value of the original and the new equilibria are identical to one another. The stress involved was a decrease in the volume and therefore an increase in the pressure of all the gases involved. What did that cause? It shifted the reaction to the right, favored the forward reaction during the period of time when the reaction was not in equilibrium. Why did it do that? Because by shifting it to the right, that counteracted the crowding effect which the stress had caused. And that's because by favoring the forward reaction, more pairs of NO2 can squash together into a single N2O4 molecule. And a single N2O4 molecule takes up less space, or is less crowded than two NO2 molecules are. So notice from the data that the concentrations of both reactants and products increased relative to the original situation. That's because the compression effect increased the pressure and therefore the concentration. It squashed up all of the substances in there. However, the ratio between the two raised to their various powers was not altered, as can be seen by the Kc value being the same before the stress and after. So what do you predict would have happened if instead we had increased the volume and therefore we had decreased the pressure? Again, the system would have responded to the stress in a manner which tends to counteract the stress. A decrease in pressure would reduce molecule crowding. So more of the N2O4 molecules would split into twice as many molecules, into pairs of NO2 molecules, and those pairs would populate the newly available space better than when they were squashed together in N2O4. And after a while, a new equilibrium would be established. In other words, the rates of forward and reverse reactions would again be equal to one another, and that equilibrium would have a constant equal to the original equilibrium constant.